Hey, Vlad here, devinsider.com, and welcome to the next video in the Scala playlist. Now, in this video over here, we've seen a few Scala's built-in types, and today we're just going to get to know a few more. As always, we're in the Ubuntu virtual machine, and we have Sublime on the left and SPT on the right running our program. So what we're going to do is, I'm just going to write a bunch of types on the left. So we're going to have val A, and the first one is byte, and then we're going to have val B, which is a short, and we're going to have val C, which is a character, and we're going to have a separate video about literals, where we're going to see all the possible ways of creating them, right? So let me just continue. We're going to have an integer, and we're going to have a long, and we're going to have a float. And by the way, notice that I'm grouping them, and there is a reason. So we're gonna have a double, and we're gonna have a Boolean, which is true, or false, and we're gonna have a unit, which is this, or alternatively also that. And now we're just gonna print them all out. Print line A. Actually, how many do we have? So if I mark them all, we have 14 lines. But we have 1, 2, 3, 4, 5 empty ones, so we have 9, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so now if I just copy these, I can just paste them over here. You see, yeah, we have all of them. Right, so save, and what do we have? Found double, required float. All right, so let's for now just do this. Again, we're going to see in the next video how to create them properly. In fact, you know what? That's how you create them. You just put an F. So today we're going to learn how these numbers how they're stored on the JVM. I mean, obviously only numbers. So we're not gonna see how a unit is stored on the JVM or how a Boolean is stored in the JVM. We don't really care. But everything else over here, they're numbers, including the character. Right, so it looks like a letter, but everything in computers is numbers, right? So what we did was we just invented a table, right? A lookup table. So we just assigned a number to every possible character, right? To every possible also there are control characters, right? The ones that can break a line or go to the beginning of the line and things like this. So we just created a huge table and we just assigned numbers. So for example, capital letter A has a number 65 and capital letter B just happens to have the number 66 and so on. So a character is also a number. So we already know that a byte is 8 bits, right? But we don't really care about this. So what we do care about is that in memory, in fact, a byte, it will literally take a byte, right? So this is how much memory it's gonna use. And I sorted them all like this, and I also grouped them all like this. Well, actually, I grouped them for a different reason. I grouped them because they sort of look similar. But in this case, in this particular group, so a short is just 2 bytes, right? And a character is also 2 bytes. And we're gonna see later the reason why they're grouped together, because there's an interesting dependency between characters and integers. Also, technically, there is an interesting dependency between shorts and characters, but we're going to talk about it later. I'm getting ahead of myself, right? So then we have an int, and an int is 4 bytes. And if you've watched my previous video, you know how to convert them into bits, right? And long is 8 bytes. For the floating point numbers, we have the same relationship between int and long as with a float and double. So we have 4 bytes for this one and 8 bytes for that one. And these are the numbers that you're sort of expected to know if you're working with a JVM. So these are not really typical, but I wouldn't be surprised if somebody would ask you that in an interview, right? At least you're supposed to know how big an int is and long and float and double, right? You might forget that short is 2 bytes, but basically it's anyway. We're going to talk about it in the next video, but basically ints are the most used one, and then if you just don't have enough memory, you just if you need a bigger number, you just go for longs, right? And the same thing goes for double. Back in the day, memory was a big issue, right? So this is why we had floats. But these days, basically, everything defaults to double. So if you need a float input number, just start with a double. But again, we're going to talk about it in the next video. I have no idea why I'm getting ahead of myself so much. All right, so we don't really care about booleans and units in this video. I just mentioned them because all the types that you see here, they're what's known as a primitive type, and we're not actually going to talk about that in detail. In Scala, they're sort of special. In Java, they're just stored more efficiently than other types that we haven't even talked about yet. But in Scala, they sort of can be both. But again, I'm getting ahead of myself again. All right, so today we're going to talk about how these numbers, these over here, how these data types, how they're represented in memory. And technically, I should also talk about these ones, but they're actually a bit more involved, and they probably deserve their own video. So I might create a video about this in the future, but not now, because now we're in the middle of the Scala playlist, and I just want to make some progress with them. Right. So in the previous video, which was technically not part of the Scala playlist, we learned about binary numbers, how about the notation of binary numbers. Right. So you might think that this is exactly how they're stored in memory. Well, they're almost stored like this in memory, but the issue is negative numbers. So let's say for now, just for simplicity, that the numbers were not stored in binary. Let's say that they were stored in decimal, and let's say that they were stored in 2 bits, right? So two digits, right? We're just talking about numbers from 0 to 99. But then you have a problem with negative numbers. So what about negative numbers, right? You have only 2 digits. How are you going to fit negative numbers in there? Well, you just divide them in half, right? So we're going to go from a negative 49 to a negative 0, and then we're going to have a positive 0, and it's also going to get to 49, right? So now we have 100 numbers again, right? So because 2 digits in decimals in the decimal system, they can represent 100 numbers, right? So instead of going from 0 to 99, we're going to go from negative 49 to a positive 49, and we're going to have 2 zeros. We're going to have a negative 0, and we're going to have a positive 0. And what I just explained to you is a so-called one complement representation, right? So later we decided that it's kind of stupid to have 2 zeros. So what we created was a 2 complement, and it's basically the same. It's just instead of having a negative 0, we're just going to have one additional negative number. So instead of starting with a negative 49, we're going to start with a negative 50. Right? So we're going to go negative 50 to 0. There's only 1 0 now. But then the positive numbers, they're just going to keep going to 49. Understanding the next bit is critical. So you should imagine them as if they were stored in a circle, right? Like a clock. You know, a clock goes from 0 to 60, 0 to 60, or 59, 0 to 59, 0 to 59, right? So if the negative 49 was over here, or actually we have a negative 50, right? So if negative 50 was here, and I have to be careful because it's mirrored for me, right? So negative 50, then we're going to have negative 49, negative 48, and so on. Then we're going to end up at negative 2, negative 1, and then we're going to have the 0, right? And then we're going to keep going, 1, 2, 3, 4, 5, and then we're going to end up at 46, 47, 48, 49, right? I hope I'm still on the on your screen, right? 49, and then if you add one more to 49, you're gonna end up at minus 50, right? And then if you're gonna add one more, then you're gonna end up at negative 49, and so on, right? So they're arranged as a circle, and you can clearly see this in binary. But again, it's gonna take way more time to explain this in binary, right? So just imagine them as a circle, and I'm gonna show you examples of this a bit later in the video, unless I forget, right? But and basically I explain all this to explain what happened to factorial and to Fibonacci in the recursion video, right? Remember, when the number was too large, all of a sudden it wasn't giving us the correct number. It was all of a sudden giving us a negative number. So this is what's known as an overflow, right? So it just went to positive, too big, and then it ended up in the negative again. Now, what you need to know about characters is that they are not stored in such a way, right? Because it's just a table, and it just go from 0 to 65,535, I think, right? So it just goes to 2 to the power of 16, right? Minus 1. So there's no sign, right? So it's called unsigned, right? So a character is stored as unsigned 2 bytes, right? And a short is stored as a signed 2 bytes. So signed is the one that I just explained was a negative one. So, you know, they have a sign. Is it a positive, is it a plus, or is it a negative, right? And character does not have a sign, so it's unsigned. So today we're just going to write a little program. First, we're going to write a few functions that convert a decimal number into a binary number, and then we're going to use that function in order to display those bytes, and in order to display the minimum value for every type and the maximum value for every type. Before we get started, I should probably say, I should probably mention a few things about floating point numbers, right? About float and double. So there's this Institute of Electrical and Electronics Engineers, and it stands for, the abbreviation is IEEE, and they have standards for a bunch of things, right? So they have a standard about how to store dates, how to represent dates, the same thing for numbers, and many other things, right? So there's a standard called IEEE 754, and it standardizes how floating point numbers should be stored. So if you're really curious about them, you should look it up. The other thing that I'm going to mention about them, that they're really dangerous, right? So calculating with them is really dangerous, and even the most experienced programmers should be really careful when they use them. It's sort of like a well-known thing in computer science. So if you do in finance, right? So if you're doing calculations with money, right? That you should not use these types. There are special built-in libraries with functions for that, right? The only thing that I'm gonna show you is this. So I'm gonna print out 0.1 plus 0.2, and you're gonna tell me why we have a 4 over here, right? And if you want to know why there's a 4 over here, again, I should probably have a separate video to explain that one day, right? But if you really want to know why today, then just watch this video over there, okay? And this is all I'm gonna say today about those numbers. Okay, let's start writing our program. So let me revert everything and just have a print line, hello world. All right, there we go. We're back to normal. So we want to write a function that takes in a decimal number and converts it into a binary number, right? And before I do that, I'm actually going to mention that Scala actually has this function built in, right? So it's called like this, to binary string, right? So we're just going to convert, a few numbers, 1, 2, 3, and 4, right? Just going to convert them to binary, and this is how they look in binary, right? And there's also the same thing for octal, and there's the same thing for hexadecimal, right? But these numbers, they sort of look the same in hexadecimal, for example, right? So let's do a 9 for octal. Or actually 8 is enough, right? Because it's only 0 to 7. So let's do an 8 for octal. Oh God, come on, octal string. There we go. This is how an 8 looks in octal, and this is how an 16 looks in hex, right? And also for hex, a 15 is kind of important, right? So 15 is an F. Right? Okay, but what we want to do is we want to write our own. Okay, so we're going to have a def to binary, just going to take an integer, and it's just going to produce a string. In fact, there's this thing called widening of primitive types, and the thing is that if you take a smaller type, it's going to fit into a bigger type, right? So even though if you're going to have a val x, right, and it's going to be 10, Scala is going to infer that this is an integer, right? So even though we're gonna be dealing with integers, right, and we're gonna be passing them into the binary function, right? Even if you specify a long, right? If you feed in, let me actually demonstrate this. And over here, I'm just gonna say hi, right? I'm just gonna show you that this compiles. So if you do it to binary of x, even though it's an int, right? We're gonna print it out. It's just going to work. So this is called widening of a smaller type into a bigger type, right? Because an int fits entirely into a long, therefore you don't lose any magnitude, so you don't lose any numbers, right? And therefore it happens automatically. We're actually going to talk much later in the Scala playlist about how exactly this is implemented in Scala. Well, not how exactly, but what mechanism is used there, because this mechanism can actually be reused for other very useful things, all right? But for now, let's just write this to binary function. Right, so let's just remove this, and let's just have that, and let's just return something just so that it compiles, okay? The function is going to be tail recursive, and you don't know what that means, and you should probably watch the video about recursion that I made a few weeks ago, right? So we're just going to have a function called loop over here, and at the bottom we're just going to call it, okay? We're just going to call it with the number that comes in, and we're just going to start with an empty string, right? Because what we want is we want to accumulate a string, right? So a loop gets along, and it gets this accumulated string so far, right? And it actually produces the string that we need, right? And then we're just going to say, okay, so if x equals 0, right, then we're done. Then just return the whatever is accumulated already. Otherwise, we're just going to call a loop, right? So this is where the recursion is happening, and in fact, it's going to be a tail recursive function, as I already said. So we're going to add the Scala annotation tail rec, and it's going to work, right? So our x is going to be something, and our aku is also going to be something. Actually, I wanted to leave this comma over here, right? So that we just have to fill this in. So our next x is just going to be x divided by 2, because in order to convert a decimal number into a binary number, you just have to keep dividing by 2, and you just have to accumulate the rest, right? So the rest division looks like this. Right, so this is, I already mentioned this, I believe, in the past. This is the common symbol to represent the modulo operation, which is the rest division, right? So all we need to do is we need to add this. We need to convert this to a string, right? And we just need to add this to the accumulated string, right? And we're almost done with this, right? So if we call this function a few times, let's call it, was a 0, 1, 2, 3, 4, and then we see that it looks almost correct. It only doesn't look correct in case of the 0, right? So in case of the 0, it returns whatever is already accumulated, but we're starting with an empty string. So there are two ways to solve this problem, and in fact, this is why it's also a typical problem in programming interviews, right? Because of this special case. So you can do it like this. So if you just say, okay, in case of a 0, I'm just going to treat it very special. I'm just going to return the 0, and only otherwise I'm going to do this whole loop thing, right? And then you're already done, right? And by the way, let's have a little fun and add an empty line and add a 73, right? Because 73 is the best number. It's palindrome 1001001. And we also want to convert it to binary, of course. There we go. All right, so 1001001. So we did it correctly. We're also going to write a different version of this function because programmers don't like special cases, and also they don't like code duplication, right? So this is a special case, and this is a duplicated code over here, right? Now we can't get rid of code duplication in one way or the other, but we can get rid of the special case, right? So we can get rid of this, right? If we just say over here that if it's 0 or 1, right? And you know, let's not care about negative numbers for now. So if it's 0 or 1, then just duplicate this code, right? So it should be exactly the same thing, right? But at least we don't have a special case, right? And I prefer this solution. And also this solution is going to help us with the next function that we're going to write. So remember that we're doing this just so that we can write a function called unsigned bits, right? And it will take a number, right? And it will tell us how many bits do we need, right? So unsigned means that you know, we're talking only about positive numbers, right? So what we want to have here is we just want to convert it to binary, right? And just say size, right? And this is how many bits it's gonna need. And then we're just gonna have a function called signed bits, right? So the ones that also contain the negative one, and it's just going to be unsigned bits plus 1, and it's gonna make sense once we start finishing writing this program, because at the end what we want to have is a table that just displays all the possible values and all the possible sizes, because right now it's sort of confusing, right? Why is it plus 1? Because in binary, right, if you just give up the half, right, it means you have 1 digit less. So let's test this. So for example, we have 73. 73 needs 7 digits, right? So if we're gonna give, we need to do this to binary, right? We just need to call this unsigned bits, right? Unsigned bits 73, and we should see a 7. Yeah, we see a 7, right? So it works, right? So for 5, no, hold on, we don't see a 5 in binary, right? So for 4, so this is a 0, 1, 2, 3, 4. This is a 4 in binary, right? So it should give us 3, right? So the length is 3. Also notice that I wrote this to binary function just to show you how similar a function would be that just keeps track of the lengths, right? So I just wanted to show you how to convert numbers to binary, right? But in this case, we actually didn't need to, right? So because we're going through the whole number anyway, right? So we could have, we might as well just keep track of the lengths instead, right? So it would be like a little bit more efficient, right? Because right now we're converting to binary and just saying, then we're saying size. But we could just keep track of the lengths while we're walking through the number, right? Let's do this real quick. Let's copy this, right? And have it over here, and call this one unsigned bits 2, and call this one unsigned bits, right? So this is the one that is going to do the same calculation for us, right? So it's not going to give us a string back, it's going to give us an int back, right? Which means that whatever we are accumulating is also an integer. So this is our sort of traversal step, right? So we still have to divide by 2 every time, right? But what we're adding up to the accumulation is not the rest, right? So we don't care about the rest. We don't need to produce the binary string out of this, right? All we need to do is we need to count, right? So if we're so basically we just need to replace this with a 1, and then we're done. I mean, we're almost done because we're starting with a 0 and that was an empty string. Look how similar they are. Right? So instead of starting with an empty string, we're starting with a 0, right? Instead of adding the rest to the accumulation, we're just adding a 1 to the accumulation, and the same thing over there. And now we're already done, unless I ruined this somehow, right? So we're already calling this unsigned bits, right? This one that we just wrote. This is also the reason why I rewrote it in such a way. All right, so let's revert that. Let's actually use this one instead of this one. And in fact, I only showed it to you just because we did a video about recursion and we did a video about binary numbers, and this is the only reason why I showed it to you. So how I would actually write it would, the fastest way to do it, instead of using our to binary, I would just say to binary string, right? And I just wouldn't write all of that. Right, and this is exactly what we're going to do right now, because now you know how to do this yourself, and obviously to binary doesn't exist anymore. So we could either do this, right, and just not have this. Oops, forgot to do it here. Right, or we can just remove all of them, and this is exactly what we're going to do. We're just going to remove all of them, right? So this is what we actually wanted. So we have two functions that are going to calculate how many bits we need, right? So let's actually start rendering the table. So we're going to have print line, and we're going to have a function called rendered signed. It's the one that we haven't written yet, and it's just going to get a name, right? Because we want to render a very beautiful table. Okay, so it's going to take the name, and it's going to take the minimum value, right? And in Scala, this is how you can obtain the minimum value, and this is how you can also obtain the maximum value, max value. And because we have our lines are getting so long, what we're going to do is we're going to do this, and we're going to do that, right? And because I know that how long this is, I know that we need a print lines of 31, right? So this is not going to compile now because we don't have rendered signed. So let me comment this out. Let me just run it real quick. Not 31, I wanted 131. There we go. So I just wanted to have hyphens that are like really long. Okay, so we're going to have this function, right? And then we're going to have an empty line, right? And then we're going to have the same thing for short. So everywhere it says byte, we're going to say short. Right? And then we're going to have a very similar thing with a char. And with a char, remember, we need the unsigned, right? So we're going to have the unsigned, right? And we're going to save it now, but we don't have render signed function yet, okay? And then we're going to do a same thing that we did to the short, right? We're going to have an int, and we're gonna do a long, right? So right now, as soon as we write those two functions, render signed and render unsigned, everything is going to be fine. Okay, so let's write them. So both of them are going to look really similar. It's just that the only difference between them is going to be that one is going to call this one and the other one is going to call that one. Okay, so rendered signed, right? It's going to get a string, right? The first string, and it's going to be a type. The problem is that type is actually a reserved keyword in Scala, right? So we can't have something like this, the same as we can't have a def or a val. We can't use the reserved keywords, right? So the typical workaround would be to either spell it like this, which I don't like, or you can use the backticks, or they're also called back quotes, and then Scala would allow you to use whatever you like for an identifier, right? So we have a string, right? And then we're just going to have min value and the max value, right? Because we see what we're passing right over here. So we're just going to have a min, which is a long, you know, remember, because of the widening, and max, which is also a long, okay? And it's going to return a string, right? Because it's just going to give us a string, and we're just going to print it out, okay? So all it will do is it will call the function called rendered, right? And it will just keep passing everything the same way. It's going to keep min and max, and then because it's signed, it's going to call sign bits on the maximum, right? And that's all that it's going to do. And the render unsigned, it's going to do exactly the same thing, right? Exactly the same thing, but it's just going to call unsigned bits, right? So now all we need to do is we need to write a function called rendered that has a very similar signature. So let me copy that. Let me duplicate that line. So it's going to be rendered. It's going to take exactly the same things, plus it's going to take the size. Let's just call it bits, right? And it's going to be an integer, right? So as soon as this thing gives us a string, everything should compile and everything should work. The problem over here is that I forgot to rename this one, right? There we go. Signed and unsigned, right? So now we have a table, but because we're always returning this, right, our table looks kind of silly, right? that's how a table looks like, okay? So all we need to do now is we need to implement this, right? And in order to implement this, the first thing that we're going to do is we're going to calculate the bytes. And we already know that a byte is 8 bits, right? So all we need to do is to do bits divided by 8, and this is our bytes. And over here we're going to construct a string, and we're going to have a separate video, I believe in 2 videos, that explains the syntax, which is string interpolation. So all we're doing here is we're building a string, right? So we're building like a beautiful sentence for this table, right? And it's going to look like this. We're going to have a dollar here, and we're going to have a type over here, right? So basically what it's telling to the compiler to do is to take this variable and just to print it out, right? So we're going to have a tab, and we're going to say a tab has bits, another tab. I already know about these tabs because I already pre-built this whole table, right? So this tab has that many binary digits, right, or bits, which is that many bytes, right? Bytes. Let me scroll up so that you see the whole thing. Bytes with another tab, possible values, right? And we need to use those variables, min and max. And if the expression is very simple, well, then we don't need the braces, right? So we're just going to do min and max. So we don't need the curly braces over here like this, as we have used with the type over here, because it's a simple expression and it doesn't have those back quotes, right? So if I did everything right, then we should see this. Yes, so we see a byte has 8 binary digits, right, bits, which is 1 bytes with possible values -128 to 127. Remember, this is the circle that I explained, so the negative number has 1 more digit because we don't have a -0, right? So a short has 16, right, 16 bits, which is 2 bytes, right, with possible values ranging from -32,768 to 32,767, right? And because a char is unsigned, it actually uses the full range, right? So it uses the whole 16 bits, the whole 2 bytes from 0 to the end, right? And a short also needs a negative number, so it has the half, right? So if you divide this, if you divide 65,536 by 2, right? So if you divide it in half, you're going to end up at 32,768, right? And the same for int and the same for long. So you see, long is basically twice as long. It's actually not twice as long. It's to the power, right? So it's way longer, right? So it requires 2 times as many digits, right? But it can display a much bigger number, right? Now it's not, the number is not, so this number over here is not 2 times bigger, 2 times larger than this one, right? It's way bigger than this. So now we're going to do a same trick for floats and doubles, right? It's going to look very similar, but we can't use this two-binary string, right? Because our two-binary string does not convert floats and doubles, and also the built-in Scala type does not do this. So we're not going to have this part over here for floats and for doubles, right? So that's going to have. I actually picked the least good one to copy, right? So we're going to have a float over here, and we're going to have a double over here. Why am I typing? I'm typing double, right? There we go. There we go. We have a double. And obviously, we're not going to call render sign. We're going to call rendered. Let's call it floating. Okay. So let's declare it. So rendered floating. It's going to be here. Rendered floating. It's going to have the same signature, right? But it's not going to do the same thing. In fact, what it's going to do is it is going to, well, it's also going to construct a string, but it's going to do this with a helper function called rendered first half, right? So the first half is going to do the type. So the first half is basically this thing, right? But it's not going to do the size, right? It's a rendered first half, and then we just have the min and the max. So the second half is going to look the same, right? Because we still have the possible values, right? And rendered first half looks like this. Rendered first half is going to look like this. It's just going to take the type, right? It's going to give a string back, right? And it's just going to do the same trick with the type. Sorry, type over here. And why did I use these braces? I wanted this braces, right? And then we're just going to have a bunch of tabs. We're gonna have 7 of them. 1, 2, 3, 4, 5, 6, 7. Okay, and we're just gonna say possible values. And I already know all of this because I already pre-built this thing, right? So if I save it now, unless I made a mistake, of course I made a mistake. All right, the maximum values are obviously floating double. There we go. Oh, and this is a very typical Scala mistake. I forgot an equal sign over here while I was copy pasting things. Right, there we go. And as we can see, I did it wrong because we probably have 8 tabs here. Right, 8 tabs. It's gonna look better. Yes, 8 tabs. Right. So this is what I meant. So the first half sort of rendered like this first half without this whole thing. It just tabbed this whole thing out just so that this thing looks like a table. Now, again, the floating numbers, they sort of deserve their own video, but because we're already talking about them a little bit, I'm going to say that you might assume that a double should be able to represent a much bigger number, right? A much bigger magnitude. But this is not what is happening, because with floating point numbers, it's all about how small the number can get, right? How precise the number can get. So what is happening over here? This is a scientific notation. So a double has way more precision bits, right? So the double can get way more precise than a float. It doesn't mean that it can represent a bigger number, right? It's not the same as with int and long, right? So with int and long, the magnitude gets bigger, and with float and double, the precision gets bigger. All right, so we're actually done, but since we already mentioned, units and booleans, let's have one for booleans. Like this. So this one is going to be for booleans, and this is going to be an empty line, and this one is going to be for units, right? And for booleans, they also don't have this first part. So we're going to have rendered first half over here. Rendered. Actually, let's have the whole string over here. So we're just going to have rendered. Yes, rendered. Nope. Render first half. That's the one that I want. So render first half with a boolean, okay, and there is no min value and there is no max value. So we're just going to do true, and we could write them ourselves, but let's actually allow Scala to evaluate them. So we're going to have that, and we're going to do the same thing for the unit. I mean, it's going to look very similar, right? So we're going to have a unit. And the unit can either be this, right? Just evaluate that, or it can actually be just that. All right. So if I did everything right, and of course I did not. Oh yeah, we forgot to close the curly brace over here. There we go. Yeah, I see what happened. So instead of curly braces, I ended up putting a quote. So now actually the highlighting is fixed, right? So this is our whole table. Actually, let me make the terminal a little bit bigger, right? So there we go. So we see the whole table. Let me save again. Yeah, so this is our whole table. These are all the primitive types from byte, short, char, and long, float, and double. Oh, actually, I wanted to have an empty space over here. There we go. Right, so let me make it bigger again. There we go. All right, so let me say it again. Okay, so now we have them as I wanted them. So we have byte, short, char, and long, float, double, boolean, and unit, and we see how big they are. Well, actually, you remember, right? So the float is 32 bits and the double is 64 bits, right? And these are all the possible values, and these are the numbers that you sort of should know. You shouldn't try to memorize them at all. But you know, sometimes you might be able to. Sometimes you might be asked about them in computer science interviews. So this is the whole code, and if you guys really want it, let me actually minimize it. I mean, now you can't read it, but you see the whole code. So this is the whole code, and if you guys want it, let me know in the comments below, and I'm just gonna put it up on GitHub, okay? So yeah, that's actually it, and the next video is gonna be about literals. So we're gonna see all the possible ways of creating integers and longs and characters and so on. And yeah, I hope you liked it, and as always, it's way too long, I'm sorry. All right, I hope you liked it, and cheers. See you next time.